Good morning, students. Today onwards, we are going to see about properties of matter and acoustics. So let me share my screen so that what are the things we are going to discuss it, and all the things I will stream it on my screen. So the block one deals about elasticity, that is introduction, a bit to Hooke's law, elastic modulus, Poisson's ratio, and the relation between elastic modulus. All these things we are going to discuss it in unit 1. And in this unit, for this unit, you can follow the properties of matter by D.S. Mathur. The second unit deals with bending of beams, that is bending coupled, plane of bending, neutral axis, expression for bending moment, cantilever, theory of non-uniform bending, theory of uniform bending, then determination of Young's modulus non-uniform bending method, and determination of Young's modulus uniform method, and the determination of Young's method by Koning's method. So three method we are going to discuss it on in this unit. And the next block, which deals with torsion of a body, that is unit 3. The expression for a couple per unit twist, work done, then torsional oscillations, rigidity modulus by dynamic torsion method, and rigidity modulus by static torsion method. So these are all some important questions. And in this block 2, we are going to deal with the surface tension. So the molecular forces, how it works, and surface tension on kinetic theory, work done in increasing the area of surface. Then pressure difference across the liquid surface. We are going to deal it with in block number 2, and some derivation parts are mandatory. So you need to get thorough with all the derivations. So determination of surface tension is unit 2, in which we are having a lot of experiments on this side. So drop weight method, angle of contact, and Fink's method, and variation of surface tension with temperature, then Jargus method, then application. So this is the unit 2 of surface tension. So these experiments are very important, as you can answer the big questions using this uh, experimental questions with the neat diagram and explanation. So unit 1 of block 3 deals with viscosity, that is streamline and turbulent motion, critical velocity, and motion of the fluids, how it works, and all these things we are going to discuss it. And in unit 2 of viscosity, we deal with the rate of flow of liquid in a capillary tube, Poisson's formula, determination of viscosity, viscosity of highly viscous liquid, Ostwald viscometer. So this is one of the important experiment, Ostwald viscometer. Poisson's formula is one of the important question in this unit. And the next unit 3 deals with Mayer's formula and Rankins method. Two important questions are there. These experiments are very easy, and you need to get thorough with the experiment. Then block 4 deals with sound, simple harmonic motion. So composition of a simple harmonic motion, and then Lissajous figures. So you are going to study it in this sound unit, unit number 1. And next is vibrations. Unit 2 deals with vibrations and frequencies. So Fourier theorem, laws of transverse vibration of strings, AC frequency using sonometer, Meldy's apparatus. So these are all experiments, and these are very important experiments also. So sonometer apparatus and experimental setup are shown in this unit. And finally, we are going with intensity and decibel of unit 3 of sound. So sound intensity and distance, decimal scale, noise pollution we are going to deal with. So the last block 5, ultrasonics and acoustics, deals with ultrasonic basic properties of ultrasonic waves, piezoelectric crystal method, magnetostriction method, and application of ultrasonics. So the production of ultrasonic waves using the piezoelectric and magnetostriction method. And the unit 2 deals with acoustics, that is the acoustics of a building, reverberation, Sabines reverberation formula is one of the important formula, and the sound distribution in an auditorium, factors affecting acoustics of a building. So these are the important questions in unit number 5 of block 5, that is unit number 2 of block 5, that is acoustics. So we shall start with elasticity. So today in our class we shall start with elasticity. So the basic law behind the elasticity is Hooke's law. So Hooke's law, which states that the restoring or a recovering force per unit area set up inside a body is called a stress, and is measured by the deforming force applied per unit area of a body, being equal in magnitude but in opposite direction. So units and dimensions are Newton per meter square. So Hooke's law is the ratio of stress by strain within an elastic limit. So that is the statement of Hooke's law. So stress is directly proportional to strain within the elastic limit. So Hooke, the scientist in 1660, uh, formed this law of elasticity, states that within the elastic limit, stress is proportional to the strain. So we shall start with the elastic modulus. Three kinds of elastic modulus are there: Young's modulus, bulk modulus, and shear modulus. So Young's modulus, which deals with when the deforming force is applied to a body only along a particular direction, the change per unit length in the direction is called longitudinal, linear, or elongation strain, and the force applied per unit area of cross section is called longitudinal or linear stress. So the ratio of longitudinal stress to the linear strain within the elastic limit is called Young's modulus. So y equal to F by A by del L by L. So the change in L length is represented in del, and the original length is represented in L. So force per unit area, which is nothing but the pressure or a stress applied. So we can say the Young's modulus y equal to stress by strain. Stress is nothing but force per unit area, that is the pressure applied, and the change in the length to the original length we call it as a strain. So this is the definition of a Young's modulus, and these materials require a large force to produce a small change in length, that is called Young's modulus. Bulk modulus, which deals with whole body get transformed. That is, the force applied per unit area gives the stress, and the change per unit volume, the entire volume gets changed. A equal to F by A. So rigidity modulus is defined as the ratio of tangential stress to the shearing strain. So it is called the shear modulus. So tangential stress by shearing strain. So let us see an animation for all these three kinds of modulus, and after that we shall proceed.
Become the master of all trades. AWS, Azure, and Google Cloud Platform. And
what are elastic and plastic deformations? Well, deformation means the change in shape and or size of the body. And the force which deforms an object is called deforming force.
Just a minute, I will stream the video.
The change in shape and or what are elastic and plastic deformations? Well, deformation means the change in shape and or size of the body. And the force which deforms the object is called force. Elastic deformation is the case of deformation when the body being in its original shape as soon as the deforming force is removed. But what really happens? In a state of deformation, there is a restoring force generated inside the body resisting the deformation. Yes, a restoring force. When the body is in equilibrium, this restoring force is equal in magnitude to the deforming force and acts in opposite direction. And as soon as we remove the deforming force, this restoring force comes into play and restores the body to its original shape. Plastic deformations, on the other hand, are the deformations that permanently change the shape of the body. The applied force here is simply too much for the body to bear, and that results in permanent deformation. Now, which objects show elastic deformation and which ones show plastic deformations? Generally, all the objects show both types of deformations. Yes, for instance, if we just keep extending the spring forever, there will be a certain limit beyond which the length won't increase further. And if we try to apply more force, the spring may lose it and end up breaking. So the spring shows elastic deformation up to some extent, beyond which it results in plastic deformation. Spring is like a common example. Generally, almost every object shows both elastic as well as plastic nature. The elastic limits depends on the deforming force applied on the object and the properties of the material they are made up of. And it is important for engineers to know the elastic limits of things such as metal beams and concrete. That is, the limit to which they can uphold the load without getting permanently deformed or cracked. Now we come to an extremely important topic, the Hooke's law. Robert Hooke, an English physicist, stated that the empirical law in 1660, which is today known by the name Hooke's law. What does empirical mean? It means the law was derived using observations. It states, for elastic deformation in a string, the deforming force is directly proportional to change in length. Consider a spring of length L whose one end is fixed from the end. Suppose the stretching force F is applied on the other end. Now let the change in its length be delta L. The law states that the force F is directly proportional to delta L. Now what do we mean in mathematics when one quantity is directly proportional to the other? It means that one thing is some constant times the other. So we could write force F is K times delta L, where K is the proportionality constant. This is the mathematical form of Hooke's law. In some textbooks, you must have noticed the presence of negative sign on the right side of this equation. The negative sign comes due to the slightly different version of the Hooke's law being followed. We can also define Hooke's law as the restoring force is directly proportional to the change in length, and this of course is valid for elastic deformation only. The force taken here is the restoring force and not deforming force. The negative sign only tells us that the restoring force is opposite to the direction in which the length is changing. Another thing is that this law is not only valid for elastic deformation in a spring, it's also valid for elastic deformation in any material. But there is an assumption that this law is valid when the forces and deformations are relatively small. Also, there is a modified version of Hooke's law. It says that in an elastic deformation, the stress experienced by a body is directly proportional to strain. Before understanding this modified version, we need to understand what stress and strain mean. And we will do that in the next video.
Okay, students, you might have understand these concepts clearly. And now we are moving to the next topic, so which is Poisson's ratio. So Poisson's ratio, it is a commonly observed fact that when we stretch a wire, it becomes longer but thinner. So the increase in length is always accompanied by the decrease in cross section, which is called a Poisson's ratio. So in other words, a longitudinal or a tangential strain produced in the wire is accompanied by the transverse or lateral straining. So Poisson's ratio actually we might have experienced when we chew a bubble gum. So bubble gum, when we extend the bubble gum, it becomes thinner and thinner. So that is one of the easiest example analogy of Poisson's ratio to explain Poisson's ratio. So the lateral strain by longitudinal strain, that is del R by R by del L by L. So now we are coming to the important question: a relationship between the elastic modulus, Young's modulus, rigidity modulus, and bulk modulus. So suppose the three stresses P, Q, and R are acting perpendicular to three faces A, B, C, D, A, D, H, E, and A, B, F, E of a unit cube of an isotropic material as shown in the figure. Each one of these stresses will produce an extension in its own direction and compression in its direction. So lambda be the extension per unit stress, then the elongation along the direction of P is lambda P. Nu is the contraction per unit length per unit stress. Then contraction is represented in nu, and P due to the stresses will be. So net elongation along the direction P equal to E lambda P minus nu Q minus nu R. Because lambda P is as long elongation and nu is the compression. So contraction per unit length per unit stress. So along P, along Q, along R we had written. And case 1 deals with only the stress P acts on and Q equal to R equal to 0. Then the linear strain E equal to lambda P, E equal to stress by linear strain E equal to 1 by lambda. Lambda equal to 1 by E. So case 2 deals with suppose the stress R equal to 0 and P equal to minus Q. So the elongation along the direction of P is E equal to lambda P minus nu the whole minus P, which is equal to lambda plus nu the whole P. So the angle of shear which is used to represent the rigidity modulus is given by the equation G equal to stress by angle of shear P by phi. So 1 by 2 lambda plus nu. Phi already we have derived it. So lambda plus 1 by nu. So 2 lambda plus nu equal to 1 by G. Then case 3 is let P equal to Q equal to R. Since the body is subject to a uniform stress in all directions, the increase in the volume is represented as 3E. Therefore, because 3 sides it got elongated. So 3E is equal to 3 lambda minus 2 mu P. 3 lambda minus 2 mu P. K is the stress by bulk strain. So lambda minus 2 nu equal to 1 by 3K. So this relating all these E, G, and K, the elastic modulus, bulk modulus, rigidity modulus, we have from the equation 2 lambda plus nu equal to 1 by G, 2 lambda plus 2u equal to 1 by G, lambda minus 2u equal to 1 by 3K is from the equation number 3. Adding equation 4 and 5 will be getting 3 lambda equal to 1 by G plus 1 by 3K. So lambda we can calculate it by 3K plus G by 9GK. Then lambda equal to 1 by E. From that we can calculate E equal to 9GK by 3K plus G. So equation 7 is the relation between the elastic constant. relating G, K and the Poisson's ratio V. So by definition, Poisson's ratio V is given by V equal to nu by lambda. So lambda plus nu equal to 1 by 2G. Lambda minus 2 nu equal to 1 by 3K. So therefore, 3U equal to 1 by 2G minus 1 by, 1 by 2G plus 1 by 2G minus 1 by 3K. Nu is equal to 3K minus 2G by 18GK. So V equal to nu by lambda. So nu equal to 3K minus 2G by 6K plus 2G. So relating E, G and V. So lambda equal to 1 by E. We know that from equation number 1. So equation number 2, lambda plus nu equal to 1 by 2G. So dividing equation 2 by 1, we will be getting lambda by plus nu by lambda equal to E by 2G. 1 plus nu by lambda equal to E by 2G. 1 plus nu equal to E by 2G. P equal to E by 2G minus 1. Equation 10 represents the Poisson's ratio in terms of elastic constant E and G. Now, K and G must be the positive quantities. The case 1, if V is positive and 1 plus V is positive, and RHS must be positive. Hence, LHS is equal to positive. So, hence, if V is negative, 1 minus 2V will be positive. Hence, 1 plus V must be positive, or V greater than or minus 1. So these are the things related to elastic modulus and the relationship between the elastic modulus, and we had derived the relationship between all this elastic modulus E, G and K. Now we are coming to the bending of beams. So bending of beams, we shall start with the introduction and we shall go for the animation for a few minutes. So beam is defined as a rod or bar of uniform cross section whose length is greater than its thickness. So for example, in a building, you can find large number of beams to support the position of equilibrium. So so as to maintain equilibrium condition, pillars are necessary. So likewise, beams are necessary to maintain the equilibrium state. So beams are subject to loads that do not induce torsion or axial loading experience compressive, tensile and shear stress as a result of loads applied to them. Okay, so plane of bending, we call it as the plane of bending is the plane in which bending takes place and bending couple acts in the plane. This is one of the 2-mark question. So in this figure, the plane of the paper is the plane of bending. So neutral axis, when a beam is bent, filaments like AB in the upper part of the beam are elongated. Filaments like CD in the lower part are compressed. Therefore, there must be a filament which is neither elongated nor compressed. Such filament is called neutral filament. So the axis of the beam lying in the neutral filament is the neutral axis. So bending of beam, before going to the bending of a beam, we shall see one video animation related to that.